Oh, it is recording. Sorry.
Okay. So, anyways, hi. So I'm going to talk today about actually doing some simulations and simulating the brain. Just a couple of quick questions before I get going. Number one, where on earth is my window that has everything? I do not like Google Meet. Google Meet does not like me. Okay. Well, I can't see anything whatsoever, so somebody give me a holler if anybody has any questions or what have you, and I do apologize for that. All right, so before we get going into this, one of the things that I know people had to answer questions about their familiarity with Python. We do want to talk about actually simulating. We're going to use Python for doing some of the simulations. So I was just wondering, and if I can't actually see anybody, I'm not sure how I'm going to do this, but I was just wondering if somebody could give if we could get some comments on Slack maybe, or something about how comfortable people are with Python. And I still can't find the window. Where is everybody? Is anybody here? Joe, am I here?
Yes.
We are.
Yes.
We
don't know if you are here, but we are here.
I think, therefore, I am, but the rest of you could be figments of my imagination.
Literally, I do not seem to have a window for this, and it's driving me bonkers. I don't know where it is. I'm going to have to quit and restart, and I do apologize because I cannot see anything.
When I had a lot of trouble with this, but there was a little picture of a few people in the upper right-hand corner. When I clicked on that, I got something a little better, but I never got everybody.
I don't see
nothing upper right-hand corner.
No, I see nothing.
And then the hamburger lower right-hand corner.
I don't see a Chrome. I don't see like.
Well, this should be the meeting details and the raise hand.
Okay, there we go. Okay. Well, this is a good start. All right. Let's try that again, sorry. But while we have this, while I can actually see the Slack here, I've been told that people are generally comfortable with Python. Is that a mostly true statement? So I don't have to worry too much about that. Okay. I'm seeing various sorts of nodding. So what I'm going to do is
people will not confess.
There you go. What I'm going to do is I have a very few slides. I'm just going to pass over them basically. But if we do need to go back to something, it'll be there. And I think that's what I'll do. And now I've got to find what happened to. All right. Now let's see if this is going to share without. I'm a Zoom person. We use Zoom all the time, and I know how to use it.
So, Robert, I
Yes.
think if you share only a tab or only a window, you can try to fit both things on your screen, like the slides and the people.
Yeah. All right. Okay, it's working now, so I can switch back and forth. And you see my screen?
Yes.
All right. Okay. So in that case, let's talk about actually simulating some brains, huh? So everything I'm going to talk today is based on Neuron 8.0. It's the current version. Most of it's going to work with older versions as well. If you're wondering why we're talking about Neuron and NetPyNE, we've sort of hinted at this throughout the day. So there's kind of a we think of this as a layered system, right? NetPyNE has a graphical interface, which is basically a level on top of NetPyNE. NetPyNE itself is just a level of abstraction that sits on top of Neuron. And at the end of the day, the Neuron is the core simulator. Neuron is what's actually doing the calculations. It's written in C, well, C++. And so all the calculations happen at machine speed. Anything that you can do in NetPyNE, you can do in Neuron. But NetPyNE is going to try and make your life easier. One of the things that I really like about the way that NetPyNE was designed, though, is that it didn't try to lock you into a system. All right, so you're free to describe everything in a declarative format and a structured format as much as possible. But if there's something that you want to do that's not explicitly implemented in NetPyNE, there is an easy escape hatch where you can say, okay, now this part of my cell specification is going to be in Neuron. So like maybe, and you'll forgive me, I don't know what all NetPyNE supports, but Neuron supports sort of a whole wide variety. So like if I have an axon passing near another axon, there could be ephaptic interactions between these two things, right? Maybe that's easy to express in NetPyNE. Maybe it's not, I don't know. But you tell Salvador you need it, it'll be fixed. But in any case, so if there's something that you don't know how to do in NetPyNE, but you know how to do in Neuron, there's an easy escape hatch. The concepts that you have so you have the full generality, the full power of NetPyNE, but with this with the full power of Neuron, but with this high level of abstraction that is NetPyNE. So you get sort of the best of both worlds. So that's why it's important to understand what's going on underneath the hood. Inside of this, and many of the concepts are going to be the same. Many of the terminology is going to be the same just because it is, like I said, a layer on top of that. But Neuron, of course, if you're not aware, Neuron's been under development for over 40 years. The name only goes back to the early 90s. But so Neuron's been around for a very long time. And so Neuron has its own graphical interface. You can do some point and click modeling. You can do analysis. It's not quite the level of abstraction that NetPyNE provides. But we're not going to go into any of this. There's over 2,000 models that have been published using Neuron. There's 700 or so that are available on ModelDB. So you can go and look at the source code and see all of that. And those are all published models that have gone through peer review, that sort of thing. But fundamentally, you know, we want to program in Neuron. We want to be able to build models. So we talked a little bit ago about just scripts in general. So a script, there's nothing to a script. It's just a computer-readable set of instructions for performing a task, right? And so in Neuron, we can use these for everything, right? We'll use them for setting up a module, we'll use them for defining and performing our experimental protocol, for recording data, for saving and loading data, for doing analysis. And like I said, you can mix and match sort of NetPyNE abstraction and Neuron low-level stuff to get whatever you need in the easiest possible way. Why do we do this? Well, if we have things in scripts, and certainly this is true for NetPyNE as well, if things are in scripts, then they're sort of automated, right? You can do for loops, you can do experiments, you get consistency, you reduce the amount of manual effort because everything can be, you make one change, you can redo a sequence of 1,000 things without actually doing any new effort. And once you have that, it makes it easier for you to swap in. Okay, well, I tested it with this cell, and now I want to do the same exact set of experiments on a different cell. Well, okay, if everything's programmatic, you can just easily swap the relevant modules out and then rerun your experiments. And again, so sort of repeated experiments. If you have a complicated experimental protocol that you want to work on, you know, again, programmatic scripts, just say, okay, now do it, now do it. Cool. Recollecting data if you do change your protocol. And then the nice thing is it's this complete reproducible version. So, yeah, by the way, I'm going to say this also. As far as Slack goes, if you have a question for me, just shout out because I'm not going to be able to monitor Slack. If you have a question that doesn't need me, just go ahead and answer, and one of the other people will be able to address it. So Neuron itself, yeah, the main website is neuron.yale.edu. You can take it there. There's instructions for downloading it on your machine. It's super easy because you can do it as a Python package if you're in Linux or Mac, and on Windows, it's just an install and download. Still pretty easy. On the top right there, there's a link to the programmer's reference. The programmer's reference, we have documentation on all of the Neuron functions with lots of examples. So here we have a function called rangevar, a method called rangevar, well, sorry, a class called rangevar plot, which basically what it does is it's a tool that you use to plot the value of a variable across some range. So if I'm doing a pseudo line scan, right? So how does calcium concentration vary in the path between the center of the soma and the distal apical dendrite, I can specify that using a range-var plot and then just pop it up in a pretty picture in my Google Colab or Jupyter Notebook or whatever I want to work in. All right. Let's see. And we've already sort of talked about, I think, Python. Personally, I use Anaconda. You can use any type of Python that you want. And if you're using Google Colab, you've got a pretty good set right there. We've already seen Visual Studio Code and working that way. All of my examples today, my exercises, for the sake of simplicity, I'm going to say, let's just use Colab. And in Colab, it's actually really easy. So all we have to do to tell Colab is this ! pip install Neuron. We tell that to Colab, and then we have Neuron available, and we can do whatever simulations and analysis we want. All right, so that's my sort of overview spiel. It really just sort of dovetails off of everything that was discussed. We saw print. Hey, look, that's how we print things. Variables, obviously we want to be able to store results, do calculations, lists and for loops. In Python, generally, of course, you don't loop over, you don't count, right? You don't say the 0th item, the 1th item, the 2th item, and so forth. You just say for each item in a thing, right? And then it's going to go through and do your analysis. So if you have different cell parts, right, you can loop over all the cell parts without having to count them. Obviously, dictionaries are great when you don't have any sort of natural order, right? There's no reason that the soma's diameter should come before or after the axon's diameter or anything like that if you have some sort of data structure. And you'll see in a bit that that NetPyNE is really based around lists and dictionaries at its core. Obviously, for any programming, functions are great. So again, I'm going through this quickly because I'm assuming that you guys already know all of this, but I just want to highlight some things. If not, if there's questions on anything, I'm happy to talk about them at more length. One of the reasons, of course, that Python is fabulous is it's this beautiful glue language, and so you can have tools like Neuron. You can combine it with like PyTorch if you want to do sort of deep learn. You can bring in everything that you want, and Python gives you this common interface to combine lots and lots of analytic tools. And so that's why it's really sort of taken biomedical computing by storm. Many useful Python modules, sklearn, of course, for machine learning. I'm going to use Plotly in all of my examples for plotting. Just because it plays very nicely in a Jupyter Notebook in a way that some more traditional tools like Matplotlib or ggplot don't, so you get the interactivity. But there's a vast array of Python modules. So just a little bit more about Plotly. So Plotly, like I said, it's this free MIT license. It's a full-featured graphics library. They have a massive collection of examples. So they have examples for everything. If you know about pandas, like Plotly plays really nice with pandas, but if you don't know about pandas, you don't need to do any of that. But so this is their basic charts, and they have, I don't know, like 5 different categories. There's a basic charts, there's a scientific charts, there's a statistical charts, and each one of these has tons and tons of examples that are associated with them. So you can go on their website, plotly.com, and just find an example and then modify it to suit your needs. Just as a very brief, so for Neuron, we'll use it in one of 2 ways. We'll either just straight up import Plotly, and then if we use import Plotly, then we'll throw Plotly to range-var plot, let's say, to say, hey, I want you to plot this using a Plotly graph as opposed to a Matplotlib or whatever. So you got to tell it what you want to graph on. But otherwise, Plotly has a variety of interfaces. The one that I'm going to use for all of my examples is this graph objects interface. So import plotly.graphobjects as Go. And then so with this, you can create a figure, and then to this figure, you can add a line, right? So this is adding line, well, a curve, right? 1, 2, 3, 4, 5 is the x values. 1, 2, 3, 4, 5 is the y values. Give it a name and maybe some properties. And then, so then there you go. So you see this blue line here. It's nice and thick that has, this is the identity graph. And maybe I'll add a second line. This is the square values. And this one's going to be dashed. And then that's the red dash lines. And then I can give it x-axis labels and y-axis labels, and I can show it. This might be a little bit more verbose than Matplotlib if you've seen that before, but the reason that I like this is because it's very interactive in these Jupyter notebooks, Google Colab, whatever. And this is really all we need to know for our example, so it's pretty easy. All right. String formatting is another thing that I'm going to show, and just in case anybody's unfamiliar with this. So in Python, if I want to put a value into a string, so let's say I have a value tstop, right? And so my tstop value is 10, right? So and you could imagine in the neuron context, right? I've run a simulation until time 10 milliseconds. And then I want to actually print that out. Well, I'll put it in a string. And the way we do this in Python is we say an F for a formatted string. And then the formatted string of, quote, we should stop at t equals. And then we just put curly brackets around whatever expression that we want to print out. So it could be a variable, it could be an expression. We should stop at t equals t stop milliseconds. So this would actually have the value of my string would be the string. We should stop at t equals 10 milliseconds. And so forth. And you can apply other formatting operators if you wanted to do anything like that. But you don't have to. Most of the time, it's just pretty easy to just sort of plop a value in. Why might you want to do this? You might want to do this if you're running parameter sweeps and you want to say, well, what parameter values did I use for my experiments? Well, I better save the parameters that I use and the file name for my data file. I need to save them somewhere anyways, and that's one place to put them. Maybe I want to label time points in graphs or label parameter values in graphs. So these are the kinds of things where we want to use these formatted strings to include values. And that's really all I wanted to, oh no, it's not, just kidding. And of course, Python, as most of you are probably aware, has a fairly extensive help functionality. So in Python, most of our time, we're going to be working with what's known as the H submodule of Neuron. So we'd load Neuron pretty much always by from Neuron import H. You'll see this over and over again, but we'll always load Neuron by from Neuron import H. We might import some other things. We'll see that in a second. But then I can, if I want to look at what all functions are available within the H module, I can say print the directory, dir of H, and it'll be like, oh, well, there's an action potential count, there's an alpha synapse, there's an ATOL tool, there's an ATOL item, and so forth and so on, and the list just goes on and on. There's a massive amount of things that are available. Once you find some function or a class that looks promising, you can then ask for help. Oh, there's an iClamp. What's an iClamp? Well, help of h.iclamp is going to tell you what there is to know about iClamp, and then this goes on and tells you examples of how to use iClamp and all of that. It's a current clamp. The I is for current. Obviously, Python docs are fabulous. Stack Overflow is fabulous. Neuron Programmer's Reference, we already pointed it out, upper right-hand corner. It's a link to read the docs. The docs are versioned, so you can see what's available for 8.0 versus whatever the latest is by the time you go to use this. We also have a Neuron Forum, neuron.yale.edu/forum. We'll take you there for neuron-related programming questions. And I'm just going to give this as a shout-out also. So if Python is new to you, because I did get some people that were like, eh. If Python is new to you and you'd like, and I know I just sort of breezed right through all of this, but if you'd like a more structured introduction, I co-taught an intro to health informatics course last summer. So almost all the information for this course, material for this course, is available at this website. In particular, on the first day, there are these 6 mini lectures that introduce Python from the beginning. I talk much slower in that. Each lecture has associated exercises and solutions. They're not going to teach you everything either, but they will give you a decent background and a good starting point to be able to understand what you need to do. This was in the context of a health informatics. So they're all health focused, but the principles are independent. And if you're interested in other sort of informatics concepts, there's more in dictionaries and that, not dictionaries, databases and machine learning. That's all up there as well, if you want to check it out. By the way, so the other thing that I want to point out is that these slides are already uploaded. If you go to the general section of the Slack, you can see a link for where the slide materials are. They're already uploaded. You can go and check these out. So if you want to find and look at them on your own pace or whatever, or go back and catch any of these URLs, they're there. So that was my whirlwind introduction to Python. I'm going to slow down after this, but does anybody have any questions or comments before we actually get started about Neuron and simulating? All right. So let's talk about Neuron. The main functionality, as I already said, is within the submodule called H. So we're always going to start out with our Python scripts by from Neuron import H. And so we'll access it. H is going to have how we define parts of cells. It's going to have how we load in SWC files. It's going to have how we add current clamps. We've already seen that, or voltage clamps, or whatever kinds of experiments. They're all going to be done through the H submodule. Neuron also has a units conversion file. So from neuron.units, I can import things like millivolts or milliseconds or microns. Those, it turns out, are Neuron's default units. So if you were to include those in your code, it's not going to actually change anything. But sometimes if you're taking rate constants from an external source, like I've done there's one of the examples that's available on Read the Docs, is a circadian rhythm model wherein protein concentrations are oscillating over the span of a day, right? And so something like that, rate constants are measured in like millimolars per hour changes. And so that you don't have to convert them, you can just use these neuron.units to do the conversion for you. Chemical dynamics, we can specify additional domains. So like neuron by default, if you're talking about ion channel, right, on the plasma membrane of a cell, it cares about the concentration just outside the plasma membrane, the concentration just inside. Doesn't care so much about the ER. So neuron by default doesn't have a concept of an endoplasmic reticulum or mitochondria or anything like that. But we can use the RxD submodule to declare these new regions to talk about diffusion within the ER, diffusion across the extracellular space. By the way, that's one way that neurons communicate, right? They have chemical synapses, they have electrical synapses, but they're also, every time that they, fire an action potential, they're taking sodium out of the extracellular space. If homeostatic mechanisms are messed up, that might matter. If homeostatic mechanisms are working, then all is well and you don't see any change. But in a pathological situation, that could be another way in which neurons interact with each other. And you can specify all of these domains through the RxD, but we'll talk about that. All this chemical stuff we'll talk about tomorrow. So you're pretty much always going to want to have import H, and you're pretty much always going to want the units, if for no other reason than it makes your code more readable. All right. So we've got 2 lines in every Neuron program. All right, we can get started at least. Here's a 3rd line that we're going to want in pretty much every Neuron program. So we can load in, you can do h.load file. So this is how we load Neuron libraries. So the Neuron has libraries that are written in Python. for which we just do a straight up import. But Neuron also has libraries that are written in this other language called Hoke. It's a much older language, but I can load them into Neuron, like h.load file std_run.hoke. And this is the Neuron's run control library. So it's the standard run system. In particular, for us, it gives us the ability to say, okay, Neuron, now I want you to run until 10 milliseconds, and then tell me where things are at. Or run until 100 milliseconds, right? So it gives us a little high-level control of, okay, now I want to run for a simulation and see what happens. All right. But I can't simulate anything unless I've defined a cell. And so how do I define a cell? Well, fundamentally, okay. So a neuron has many pieces, right? And so we've got a soma, we've got an axon, and let's say the axon, for example, can be decomposed into there's a piece from the soma out, and then it branches, and then it branches, and then it branches. So it's a whole bunch of unbranching sections that are, you know, connected end to end. And so in Neuron, each of these unbranching stretches is called a section. All right. And then, you know, the apical dendrites are a collection of sections that are connected in some way. And so how do we create a section? Well, we create a section using h.section. So if I want to create a thing, I'm going to create a new thing called a new section. I'll give it a name, apical, and I'll give it a variable, a Python variable, apical. It's always nice if your name matches your variable. There are reasons why this isn't always going to be the case. But in any case, the name here is what prints out. So if you print out the section, it'll say whatever's there, right? So it'll just say the name of the name that was assigned to the section. But I can have, of course, multiple references to a section. You can imagine I loop over all the sections of a cell. So I have the original apical and then my loop variable, which is sometimes pointing to the apical and sometimes not. But so fundamentally, everything in every neuron can be decomposed into a bunch of sections. Does that make sense? A section is where stuff is. Cool. All right. And a section has various properties, right? A section has a length. So if my section is a soma, then the length of that is soma.l, capital L. The diameter is soma.diam. I might chop that section into pieces because numerically what we do is we just say, well, we can't calculate, technically speaking, the membrane potential is not constant across any section, any length of dendrite. But we cannot calculate infinitely many different values because the computer only has finite amounts of memory. So what we do is we take our section and then we say, well, maybe I'll just calculate one variable for the first third, and then one value for the second third, and one value for the third third. And that'll be the membrane potential in each piece. All right, and so in Neuron, we specify how many segments that we chop each section into with this inseg variable. So soma.inseg lets us specify how many pieces. So here it is, if I have one continuous length, and then so inseg is 1, I calculate the value at the middle. If I were to have 2 pieces that I break it into, then I calculate the value at the middle of each. If I have 3, then I calculate the values at the middle of each. And what I want to point out, by the way, you'll notice that when I went from 1 to 3, I had a node here in the middle of the entire thing. And then when I went to 3, I had a node in the middle of the entire thing. And if I were to go to 5, I'd still have a node in the middle of the entire thing. As long as I have an odd number of sections, first of all, I have a node at the middle of the thing. And if I increase the number of sections I have by an odd factor, all of my old values, all of my old locations that I calculate continue to be valid locations. Versus if I were to increase it by an even factor, I start out with a node in the middle of this thing, but now I no longer have a node at the middle of my section. So as long as I increase by an odd factor, I can do sort of convergence tests. A lot of you are like engineers and mathematicians. You should love convergence questions, right? What happens? Has my cell started to converge with my spatial discretization? Well, just increase it by an odd factor and check at the at each location. And so once I have multiple sections, I can connect them using the connect method. All right, and that lets us build arbitrary morphologies. Now, I'll show you that in a second. But so fundamentally, a fundamental unit of a neuron is a section. And we can loop over the sections. So if I create a section, here's dend is h.section, name is dend. And it has a certain length and a diameter and an inseg. I can loop over my section for seg and dend, which is my section. When I'm looping over that, that's hitting each segment. And so since inseg is 3, I'm going to print out my 3 locations, print seg. So I'm starting out at 1, 6, 3, 6, and 5, 6, which is the centers of each of those. And then I'm just having it print out the area of the segment. And they're all the same, of course. 2 pi in this case. And you can do the math to convince yourself that each one should have surface area of 2 pi. I can, however, change properties. So let's say that I want to change the middle one's diameter to be 4 instead of 2. Well, now all of a sudden, the surface area in the middle segment is 4 pi instead of 2 pi. But so the segments can have different properties. That's fine. They are supposed to have different properties, right? They have different membrane potentials. They can have all kinds of different properties. But yeah, just want to point that out. We can note that we can access a specific location by taking a section and then parentheses and then a location. So 0.5 is the middle. Okay, so what we do in each one of these sections here is I'm going to use normalized distance. So instead of measuring from 0 to the physical length of the section, so maybe the apical dendrite's 100 microns long. And instead of saying I'm going to go 50 microns down, I'm actually going to normalize all of my sections between 0 and 1. And then, so then dend of 0.5 is the middle location within the dendrite. And the reason for this convention is that this allows us to say, oh, okay, well, we tested it on this cell's dendrite in the middle. What about this cell? Well, that cell looks different. But, well, we can still have a concept of the middle. We don't have to change the length. We don't have to worry too much about that. And we can ask for a specific segment by just dend parentheses 0.5 gives us that segment. The segment containing the middle position. And then once I have a segment, I can ask questions about it, like what's the x-coordinate, what's the normalized position in the segment? Well, it's the 0.5 point, because that's what we asked for. Which section is associated with it? Is the segment section the dendrite? Well, yes, it is in this case. And the one other thing that I want to point out, so I'm presenting all of this stuff as if it was cylinders. It doesn't have to be cylinders, of course. Neurons are neurons do not look like cylinders. Sometimes there's tapers, right? Sometimes a dendrite might taper off. That's fine. We can specify this manually with what's known as 0.3D add. So we'll say an X, a Y, a Z, and a diameter. So here's a dendrite that passes through the origin at diameter 1 and passes through the point 10,0,0 with diameter 5. And that's fine. And it'll do the right thing. It'll be this frustum. And it'll calculate the volume, and it'll do all the surface areas, and all of that will work. Now, obviously, we don't want to do too much of this ourselves because that's going to get very old very fast. But fortunately, we'll see that we don't have to. But we could.
I have a quick question.
Yeah, please.
So can you explain the difference between a segment and a section?
A section has many segments.
Okay.
And also,
And then so is a segment just like a individual kind of sliver?
Yeah,
In
a
this case
segment
of the
is
dendrite?
a, I'm sorry? I cut you off a little bit.
Oh, no, it's like, is it like a sliver of the dendrite?
Yeah.
Okay.
So in the sense of it's a place where we calculate one unique value for every state variable. So if we have a Hodgkin-Huxley, right? So Hodgkin-Huxley has 4 state variables: a voltage, an M gating variable, an H gating variable, and an N gating variable. So we'd have, for one segment, we'd have one value of V, calculate the middle, one value of M, calculate the middle, one value of H, calculate the middle, one value of N, calculate the middle. And we're going to assume that it's effectively the same throughout.
Okay, thank you.
Yeah. And so if I want
something similar.
Yeah, sorry, go ahead.
It's something similar to a compartment.
Yes.
And, okay.
Yes. So a section, think of a section as a physical entity, right? Like it's this long stretch of apical, right? It's where the apical goes from here to here without branching. But this a long stretch, I'm going to want to do it in multiple pieces.
So you also mentioned nodes, and each section is divided into 3 nodes, right? I
use those words, and I use node and segment interchangeably. They're not quite, but for all practice, but I meant segment. There is a minor pedantic note difference between a node in Neuron and a segment, but it does not come up yet. And so we'll see, nodes and neurons are used for chemical entities as opposed to electrical, and it matters because chemical stuff may have different discretizations because it has different space constants, right? A chemical gradient may be very sparse, but electricity spreads quickly.
but in the previous slide, there's like 3 nodes for one segment.
No. If I said that, I apologize. There's 3 segments for one section.
Okay. Can I go to the previous slide, please? And the right side, you said like n segments equals 1, and then there's like those 3 dots. Are those, what are those?
Okay, so
sorry.
So there is a 0th position, a 1th position, and then there's the middle position. And this is a location. So voltage in Neuron is always calculated at the ends of each segment. There is an exact, voltage in Neuron is always calculated at the ends of each section. So at the 0 value, there's a voltage. At the 1 value, there's a voltage. But the only state variables other than voltage are only calculated at the middle of a segment. So when there's
Robert, it might be worth saying that there's a real motivation behind having sections and segments. Sections are any unbranched neurite. So a dendrite, an apical dendrite, can be a single section that's hundreds of microns long, but you would never want to treat that as one compartment or one segment. So you subdivide it into segments. And what this allows is that you can test spatial accuracy of your numerical integration in the same way you would test your temporal accuracy with change in dt. Here you effectively change the dx of your partial differential equation of your numerical integration by changing the number of segments in this long unbranched section.
I agree.
Is there something like a sensible, say, sampling rate for a given whatever cable length?
I'm sorry, what was the question?
So how many segments do I want per, say, micron of cable?
So Neuron provides this thing known as the Lambda Rule. There's a library. I don't know if it's in the slides, but that basically Neuron provides a library that will calculate this value for you. And so that's based on an analysis of the ion channels that are present. So it has to do with the electrical space constant. If you want a quick and dirty rule of thumb, I generally try and go for about 20 microns per segment, with the insistence that I always have an odd number of segments. But the D lambda rule will give you a more principled approach. And if it's not in the slides, I will share it, I guess, on Slack or something. How to do
And
it.
I guess there must be an incentive to sort of keep this constant across the neuron, right? So I don't want to have whatever.
Oh, so, I mean, well, you're going to want to have, what do you mean?
No, that's what I'm asking. Do I want to keep this constant across the neuron, or do I want to sort of oversend
No,
it?
you don't want to keep it. You don't want to keep it constant, because certainly the soma is isopotential. So even if it's a very long soma, you really only need one segment, whereas a thin dendrite might be the same 30 microns long as a soma of a pyramidal cell, but you'd want to divide that up into multiple segments. So no, it's not the same.
So if you look at, for example, in this picture here, we have in the top left, we have a cell. It has many long stretches, and then we've sort of blown apart, we've disconnected it every place where there's a branch. And so each one of these long stretches with possibly varying diameters is a section. And you could imagine, certainly we want more compartments in the long stretch than we do in the short stretch. So that's why I said, as a rule of thumb, what I personally go for is, if I'm not using the D lambda rule and I just want to do something quick and dirty, about one segment for every 20 microns. But again, you can do a principled approach using a library, and if it's not in the slides, I will add it to Slack. But does that make sense? I mean, it's really about the length. It's not about the number of, it's going to vary because it's about how quickly voltage changes.
Yeah.
All right. So once we have a section, then we need to connect sections together. And so the way that we connect sections, as I've hinted at, is the connect method. So if I have a section DIN2 and I want to connect it to the one location at DIN1, that is to say the end of DIN1, it'll put the 0 location of DIN2, boom, smack at the end of the one location, smack aligned with the one location of DIN1. Okay, and if you could imagine, if I were to have a DIN3 that I also connected to the one location of DIN1, now all of a sudden I have this Y-shaped cell. So here's an example with inconveniently tiny text. I do apologize for that. But if I have a bunch of sections, you could load from neuron import H, because we're always going to do that. I can load create a bunch of sections. Soma is H.section, name is Soma, and so forth. Then I can connect them, right? So I'm going to say the proximal apical is going to be connected to the soma. If I don't give a location, it's going to assume that I'm going to connect the beginning of something to the end of the guy. So the one end of the soma is going to be connected to the proximal apical. The one end of the soma is connected to the proximal apical. The 0 end of the soma is going to be connected to the proximal basal, so the opposite side, right? The apic 1 and apic 2 are both going to be connected to the proximal apical on the far end. So then I end up with this this branch location here. Does this kind of make sense? I do apologize for the font size, but the slides, like I said, are available on the drive. But in any case, so I can connect a bunch of sections together, and then I can start to build an actual neuron. Just like one neuron can be decomposed into a bunch of sections, and then the connect method is how I put them together. Does that make sense? All right, cool. Of course, sections are going to have length and diameter and position. We've already seen this, I guess, now that I realize this, but the length is .L, so the section, sec.L, if that's axon, let's say axon.L is 20 microns. Sec.diam is 2 microns in this case. Here, UM comes from neuron.units import UM. And again, if you don't specify units, neuron's going to assume microns, so it's no biggie. Yeah, and we already saw we can specify 3D locations with X, Y, Z's, and diameters if we want to get creative and get the wiggles and the curves around, and it's not just a stick figure. One key word of caution, though, if I do nothing, if I do nothing, if I just create a section and I don't specify a length and I don't specify a diameter, well, it's a chunk of neuron. It's got to mean something. Well, it turns out, though, because Hodgkin and Huxley were sort of the founders in some way of modern computational neuroscience, everything's based on what Hodgkin and Huxley had. And they worked with squid. And particularly, they worked with the squid giant axon. And the thing about the squid giant axon, you'll never guess, it's big. And so in particular, the squid giant axon, so that neuron's default has a diameter of 500 microns. That's great if you're a squid, helps you get away from that predator. That's why you need the big axon. But mammals, we don't do that. I think Bill talked a little bit about myelination and nodes of Ranvier. We've got our own cheat codes for sending things, messages faster. And we don't need to do this whole giant axon thing. It turns out they take up a lot of space. Right, so all of the parameters that you see in Neuron are defaults are based on squid. So the diameter is 500 microns. The axial resistivity is 35.4 ohm centimeters. If you're talking about a mammal, though, it should be more like 100, right? The temperature is 6.3 degrees Celsius. Again, if you're talking about a mammal, you're going to have a bad time at 6.3 degrees, right? So you're going to want to set all of these things, or you're going to get surprises. Also, if you're doing a mammal, don't use Hodgkin-Huxley because they're, they work best at 6.3 degrees. But so in any case, so beware of neurons units. The one other little tip I want to give you, just when you're defining cells, it's generally easiest. You guys know Python, then you probably know about classes. It's easier to define classes of cells rather than individual cells. So a class is just a way of defining. This is the concept of a pyramidal cell, right? And every time that I create a pyramidal cell, it's going to have a soma. And that soma might have a certain properties, right? A length and a diameter, or what have you. And so we can assign all of these things, and we associate this class of objects, this class of pyramidal cells. And if I run that code by itself, it does nothing because I've just defined this is what a pyramidal cell is. But the beautiful thing about that is then I can just go and I can instantiate it, right? PYR1 is pyramidal, open close parentheses. And now I have a pyramidal cell that has a property, pyr1.soma. I can then ask for that pyr1.soma.diam, and then so the diameter is 10 microns. Default unit for distance is microns in Neuron. So that's cool. That's all well and good, but that's now added 2 extra lines. But the reason that we do this, the reason that we want to build cell classes, is because if I can do 1, then I can do 2. I can make another guy, right? PYR2 is pyramidal. And whatever complications that I put in that initial block, in that constructor for my cell class, well, that's going to apply for my second pyramidal cell, right? So however complicated of a cell that was, I can make a second copy, boom, in 1 line. Or, because this is Python, I can use a list comprehension and make 1,000 of them in 1 line. And then we start to get nice, right? So that's the advantage of defining classes of cells. So you might imagine you have a class of cells that are pyramidal cells, a class of cells that are basket cells, a class of cells that are chandelier, or whatever your favorite cell types are. Define a class of cells. They have certain properties, certain morphologies, certain ion channels, and then you can stamp out as many copies of these as you want. One tip that I'm going to give that I didn't show here, but I think I show in some of the later examples, for the sake of doing a network, I do put it here, actually. For the sake of building networks, it's often convenient to number the cells as you create them. So this is cell 0, cell 1, cell 2. So you can talk about, well, cell 7 projects to cell 3. You can do all of that kind of stuff. But we'll talk about networks later. But so in any case, classes are great. They allow you to make multiple copies. So here, for example, let's just say that I have a cell class, class cell, and here's what's going to happen. Every time that I make one of these guys, it's going to have a main section, a den1 and a den2. Den1 is going to connect to the main, den2 is going to connect to the main. So I have two sections that are connecting to the end of a third section called main. And they're going to have certain properties. And then I can store, it's often convenient to store like self.all, which is, here's all of my sections. So just so that you can easily grab it. If you want to say everywhere in the cell, there's going to be Hodgkin-Huxley channels, or everywhere in the cell, there's going to be a leak channel. But this is also easy to get in general. If I have any section, so the main section or the soma, it's often the soma, right? If I have but any section, if I have any section of a cell and I say .whole tree, it's going to return a list of every section that's attached to it and attached to its children and so forth and so on. So the whole tree, if I start with the axon, if I start with the soma, if I start with the most distal of apical dendrites, doesn't matter. Whole tree is going to give me all the sections that are attached to it that form the same cell. All right, but in any case, so I've defined this thing. I can instantiate it. So my cell is open close parentheses on cell. I created a copy of it. And so here's some more Python magic here. So in Neuron, we have this concept called a plot shape. So h.plot shape. What it does is it plots the shape of the cell. Okay? So h.plot shape is how we look at what the cell looks like. And there's not a whole lot to see here because I got one section and I got two things that are attached to it. But sure enough, if I do this, h.plot shape, and then I tell it, oh, I want you to plot this on Plotly, and then show it. So this returns a Plotly figure. So I could keep sending this on to plot more and more things if I wanted to. But Plotly figures we can ultimately show with .show. And so what do we end up with? We end up with this cell here. Hey, look, there's one section and it's got two things coming off of it. And if I wanted to save this to a PostScript file, there's a print file command that'll generate a nice pretty picture that you can use and embed it in publications.
Sorry.
Yeah.
And what about the orientation of the branches of the section that you add?
So what happened? So since I didn't specify here, Neuron just made a choice. If, on the other hand, remember that I have this thing called point3d add. You remember that? So I said point3d add says I have a branch that is at this 3D point, x, y, z, and has a diameter. And then I give it another 3D point, x, y, z diameter. And then that's how I specify orientation and curves. So I can give it actual x, y, z values if I care to. And you can imagine, there was a question earlier on the Slack about SWC files and importing morphologies. Right, that's what happens internally. The SWC file is just a list of x, y, z's diameters.
Sorry, and the orientation is the same for the whole section, or the different segments can have different orientation?
Well, it's not even segment spaced. I can have as many 3D points as I want.
Ah, okay.
And they can be spaced however I want. And so
you make a trajectory if you want.
Absolutely, and we'll see that in a little bit with imported morphologies from Neuromorpho. I didn't want to do that personally because there's only so many points I feel like typing out.
Okay.
You know, it's much easier to load a file. But before I do that, one other thing. So the reason for this, so this is all nice. It's a pretty picture. I see what it looks like, but wait, what? All right, hold on one second. I'm mildly confused. Oh, yeah, here we go. All right, so if I were to assign voltages, so the way that we assign voltages, I can say I have my cell class, so my cell.main was my section, and then each section has a .v, and in particular, each segment has a .v, so the segments can have different membrane potentials. But I can set them, if I just assign them to the section, it's going to set it everywhere. All right, so I'm going to say everybody within my main section is going to have a membrane potential of 50. Again, neuron defaults to millivolts, but if you don't specify. My DIN1 is going to have a value of 0 millivolts. My DIN2 membrane potential is going to be negative 65. And then when I go to my plot shape, I can give it some other parameters. I'm going to say, I want you to plot the variable V. V is for voltage. It's the same thing that I passed right here, right? Main.V, we'll plot V. And then what's my color range? My color range is going to be from negative 80 millivolts to 80 millivolts, which is probably bigger than I should have used. But in any case, so then I can plot this, and I see that each section gets a different color. If I can specify alternative color maps and all of that jazz by passing in a CMAP argument. If you know about color maps, there's a whole theory about how to make things that convey information and don't mislead. The big thing you need to know is don't use jet. But in any case, so this lets me see a heat map. So I can look at a cell. If I have a cell morphology, I can look at it and I can say, oh, well, this parts of the cell have gone above threshold, whereas we never get any significant membrane potential elevation out there. So you can look at this all. You can look at this all on the big picture. And by the way, so I'm showing this with as a static image because it's a picture. But if you're running this inside of a Jupyter Notebook or something like that, a Google Colab, you know, you zoom in, you pan, you tilt, you rotate everything. It does all the stuff that you'd expect it to. Right, it's a very interactive graph. And we'll see this. We've got some exercises coming up later tonight. We'll see this in the exercises. One of the exercises is going to be to just, okay, well, load a morphology from NeuroMorpho, and then play with it and see what you can see. That's coming up in 2 slides. Also, again, range var plot. So there are 2 main types of neuron graphs. Everything else is like, you know, Plotly is gonna, you want a bar graph or for some reason, or you want a pie chart, or you want whatever. Plotly has that, right? Like those are standard graphs. But there are 2 neuron-specific types of graphs. Okay. The first one is just being able to look at the cell. You can't look at the cell; it's really hard to know what you're doing. There. The second one is this range var plot, which is what is the path, what is the concentration or membrane potential, or whatever variable you're interested in along some path between 2 points. And so the way that we do that in Neuron is, like I said, we use this range var plot. We saw that earlier. It was my example. What variable do I want to plot? We pass it in as a string. So the string V for membrane potential. And where do I want to go? Well, I want the path between the 0 end of main to the 1 end of DIN2. And if you look back at our notes, what we said is main everywhere is 50 millivolts, and DIN2 everywhere is negative 65. So then when we do this and we plot this, again, I'm plotting with Plotly. If you prefer to plot it on the Matplotlib, that's cool. But so if I'm plotting this onto Plotly, it starts out at 50, 50, 50, 50 for a length of 100. I guess I didn't set that, but that's the Neuron's default section length. So it's 50, 50, 50, 50 until it's negative 65, right? Because that's where we switch from main to DIN2. This is the 0 end of main. This is the 1 end of DIN2. And so this is showing us the membrane potential along that path. And because we haven't actually done anything, it's a square pulse. If we let time advance, right, obviously it's going to start equilibrating because they're connected. So that's the second fundamental neuron-specific graph type, right? So it's what does the cell look like? What's a path along the cell look like? And pretty much anything else that you want to do is just going to be built on top of any sort of standard graphs that any regular graphics package is going to have. And just for the record, so I'm showing voltage. So there's every segment has a .v for the voltage. And if I'm passing this to plot shape or range for a plot, I'm going to pass in the string V. There's a convention as to how we do ions, right? So for sodium, Na, the concentration inside, I for inside, is the segment dot NaI, is the concentration inside, so then I pass NaI in the plot shape or range for a plot. The concentration outside of the membrane is NaO, O for outside. If it was potassium, it would be Ki, the inside potassium, and Ko, the outside potassium. If there's a current, it's INA, IK, ICA, ICL, whatever ion you're interested in. If you care about the reversal potential, so assuming you're using sort of a Nernst type of environment, there's a seg.ENA. Yeah, so that'd be the sodium reversal potential. EK would be the potassium reversal potential. ECL, the chloride reversal potential, and so forth. And these things exist exactly where they need to. Okay, Neuron is not going to calculate the magnesium concentration unless you need a magnesium concentration. That would be a waste of processor power, right? So, but this is also true for sodium or chloride. So if you don't have a chloride channel, you don't have anybody that uses chloride, and there's many ways that somebody could use chloride, but if you don't have anything that uses chloride, don't ask it for the chloride. It's going to be like, I don't know anything about that, because it doesn't, because why would it? It only monitors whatever's in your model. Does that make sense? All right. So does everybody see how this sort of generalizes to other things? Okay. The one other thing that I want to point out here, and we haven't gotten to this just yet, but we're going to talk about recording values. And recording values, so seg.v is the membrane potential now, right? If I want to record the concept of membrane potential, I need to think somewhat more abstractly, right? So membrane potential in the center of the soma, right? Membrane potential in the center of the soma is a thing that varies over time. I can't pass the value now, which is a number, to a function to record it. I need to pass instead what's known as a pointer, which is basically the memory location that stores the soma center membrane potential. Because I'm going to record the values at the center of the soma, not a specific number. And the convention in Neuron, basically, the long story short, is we just add this underbar ref underbar before the variable name. So if seg.v is the voltage now, if I want to record it or feed a value into it, it'll be seg.underbar ref underbar v. And that gives us what's known as a pointer. They're just as powerful / dangerous as they are in any other programming language. Use them wisely. But as long as you use them wisely, they're harmless. And we'll see this. I'll have examples of this if this doesn't make sense to you. If you've seen pointers before, hopefully you're good. If this doesn't make sense to you, we'll see examples of it shortly. Any questions on any of this so far? All right. That then being the case, we've hinted at this. We've seen morphologies. Let's look at it. How do we actually do this? So if I want to load a particular morphology, so let's say I have some SWC file, and you say to yourself, well, where do you get those SWC files? That's not my problem. No, I have an answer for you. But you want to load some morphology that somebody, hopefully you got a buddy. You got a buddy in the lab who loves playing around with Neurolucida and has done a recording and has measured a whole bunch of points. They've clicked the mouse a lot. Okay, well, the cell's there, okay, and the diameter is about this with the scroll wheel. Click the next point. Okay, click the next point. Repeat a few thousand times, and then you have a neuron reconstruction. Couldn't be easier. But so in any case, so however you come across one of these files, so you have some morphology. Let's say this particular one, C91662, and I actually use it in the exercises. So from neuron import H, because we're always going to need this, we're going to load, we actually don't need stdlib anymore. We used to in older versions. We're going to load in import 3D is our library for importing a 3D reconstruction. The names make sense for the most part. So we're going to load in this import 3D library. And so here's how we're going to do. We're going to define our cell class. And so, you know, I like to keep as little as possible in the constructor. That's just me, but it helps me sort of make my code self-documenting, right? So I'm going to have just one function call in my constructor. It's going to load the morphology. And then, so then this one little bit with these 4 lines is how I'm going to load in an SWC file. And if I wanted to swap out, and the reason for this is if I wanted to swap out a morphology later, I want to swap out the cell function, and I'm looking through my code, oh, well, it's going to be in that load morphology. I know exactly where to look. It's a relatively small thing. It's not one giant function. So if I break everything into little itty bitty pieces, it's very easy to do. So in reality, so I'd have like a load morphology. I might have a do discretization. I might have a insert ion channels. Remember, we don't actually have any ion channels yet. They're coming. But that sort of thing. I'm just going to break each one of these things into pieces. But in any case, so I'm going to load my morphology. And all of my loading of morphologies are stylized. You can just copy paste this code and swap out the file names. It's not going to change. So I'm going to, once I've loaded my import 3D library, I get this tool called h.import3d swc read. You might imagine, and you'd be right, there's also a tool called h.import3d neurolucida read, etc. I think there's a eutectic read. So we have a whole bunch of different readers, but SWC is pretty widely available, so I just give that as my example. So I'm going to load in this reader. It needs to input the file, so you just pass in the file name. And then you're just going to use construct the tool. So you pass in your reader to the import 3D GUI tool. Don't get hung up on the name. It doesn't actually make a picture if you pass. It has this, okay, import 3D GUI has a graphical interface that you can use to edit the picture, you know, look at it. Is this right? Do I need to edit it? Do I need to join points? Is it making the right assumptions? Is it interpreting the file correctly? And it'll yell at you if there's some things that are problematic about the file. But we're just going to not do that. So that's what the false argument's for. And then i3d.instantiate self just means that it's going to create it within this pyramidal cell instance. So PYR is pyramidal. Boom, I have one of these. It looks, you know, it looks like this. And I've loaded in the morphology. If I wanted a second one, cool, I can do that because that would be like PYR2 is equal to pyramidal. And then I'd have a different one. It's completely independent, has its own state variables and everything. But I can construct these arbitrarily complex cells, now as many copies of them as I want, with one line. This is why classes are great. And I'll add that when you do this instantiate, it creates some sections within the object. So pyr.apic is going to be the apical dendrites. pyr.axon is going to be the axon. pyr.soma is going to be any sections that are tagged as soma. This depends on how well, you know, this assumes, of course, that whoever created the SWC file annotated it correctly. So, you know, you're dependent on whatever they labeled it. But in any case, you get all of these things and you can query them and they give you reasonable names and everything good happens. So do you find yourself saying, well, yeah,
Robert, sorry, this file, this structured file should be in my computer, or should I, or can I just upload it directly from the internet?
C91662.swc, that particular file, or?
No, whatever file I want.
But the morphology file is
yeah.
So the morphology, so this is set up to load it locally. Yes.
Okay, but can I use a pointer? I mean, define the address where the morphology is stored, and then call it just passing by the address. Yeah, the URL.
So what Python allows you to do is Python allows you to load URLs. So there's the request library in Python allows you to load in a URL, and then so you can have it so that your Python script always starts out by loading in the morphology
Okay.
and then saving it to a local file. Neuron does not know about the internet itself, but but you can use Python to load the file, save it locally, and then import it.
Okay, so it's feasible, but it requires some tweaking.
It requires some tricking, but like that some tricking is like 3 lines of code.
Okay.
Because it's Python and everything is like 3 lines of code max in Python.
Yep. Thanks.
Okay. And so if you want it, so here's my, one of the great resources that we have available so that you don't have to stare at a in a microscope and click 1,000 times to trace the morphology. Neuromorpho.org is a wonderful repository, well over 100,000 neurons, well over 300 brain regions, representing a massive, massive amount of effort of other people. And that's the best, right? If you can have other people do all of this stuff. They've been so kind as to share it. And so what happens is if you go to Neuromorpho, there's over 500 different cell types. They're all there. And you go into a specific entry. This is C91662, just to keep with my theme here. And you go into that specific entry, you're going to see a ton of metadata that's associated with it. This comes from a rat, a Sprague-Dalley rat. It has certain properties. The rat was at least 33 days old when this cell was taken. And so the morphologies come however they come. So every entry has this original morphology file, and it could be anything. It could be Neuralucida, could be Eutectic, could be SWC, could be something they made up. Doesn't matter. But one of the things that Neuromorpho does that's really convenient is that they've standardized everything in the SWC. So the morphology files standardized are always going to be available in SWC. And that's why I'm using SWC as my default example, because it always exists if you're getting it from Neuromorpho. And Neuromorpho, if you go and you browse the website, they have tools, I think LNeuron, that can help you convert file formats into SWC if you do have something that's not available in that format. But like I said, Neuron supports all of the stuff. Just search our documentation or give us a holler. Yeah. The one thing that I'm going to say, by the way, on this, when you take a morphology, and this is one of the reasons that we're talking about this from the neuron context, because this is 100% is true in NetPyNE as well, right? If you take a morphology from somebody, they might not have been preparing it for the sake of doing computational neuroscience simulations. They might have been measuring the change in branching rates in Alzheimer's models mice versus non-Alzheimer's model mice. That might not be suiting your needs, right? And so if they didn't care about the diameters, you'll find a number of things in Neuromorpho that don't have realistic diameters. You'll find some things in Neuromorpho that aren't 3D, that are flat. They try to label these things. It's always good, however, to check. You'll find some things that have sort of weird shrinkage artifacts or z-axis errors or whatever. And I'm telling you this not to put you off on this. It's a fabulous resource. I'm telling you this to be aware of this because they're solving a different problem than you are. And any time that you're trying to build on somebody else's work, which is always, because that's what science is, right? If you're trying to build on somebody else's work, you got to look at it to make sure that it's useful for your needs. All right. And so you're going to need to look at it. You're going to need to spin that cell around. You're going to need to try maybe injecting some membrane potential, injecting some current to see if it spreads to the whole cell. Is it all connected? Are the diameters constant? Are they varying? Are they reasonable? And so you're going to want to check all of this stuff before you use somebody else's morphology, because if the diameters aren't reasonable, then and you're trying to do a realistic neuron simulation, well, then it's not realistic. If there's z-axis errors where all of a sudden the dendrite jumps 20 microns in the z-axis, then what are you gaining by choosing a reconstruction that has that kind of an error? Because you're now just introducing, you know, you might as well use, it's now not a valid simulation. Does that make sense? So just make sure that it's reasonable, because it's not always, you know, they have their own purposes, and this is true for everything. All this science exists, they're doing some context, and you just got to look at it. All right, but so let's say that I've got one of these cells, and so I constructed a pyramidal cell as before, and so now I want to create 10 of them. All right, and so we know from, you know, Python, and if pyramidal is a class, then I can instantiate one of them with this open close parentheses, and then I can use a list comprehension to make 10 of them. And I look at them in a shape plot, and here are my 10 pyramidal cells. And how do you like my 10 pyramidal cells? What happened?
Are they all exactly the same? So
Yeah, because I'm loading in an SWC file that says I have a cell whose dendrite goes through this point, X, Y, Z. And another dendrite. So every time they're all going through the same X, Y, Z points. Well, is that a problem? Yeah, it depends. It depends. But certainly it's not a very convenient thing to go to your advisor and say, all right, so I constructed 10 cells. See here. Right, so that's not very helpful. So what you can do, and here's some code, and again, that's on the slides, but here's some code, and what it does is you pass in an X, Y, Z, and it's going to shift everything by a little bit, right? And it's just this point 3D change. It's this loop in the point 3D change that's going to shift it over a little bit, and then that's it. And then now you can instantiate them and put them in different places. You could imagine that if you were so inclined, you could add rotation. You could do whatever kind of math you want. But if you want to just look at things, you know, at least spacing them out is going to make you happier. So does this?
Robert,
Yeah.
Can you just ask, have you got code? So presumably you can change these parameters when you're creating a class. You can make the parameters like such that they fall within a certain range of values with a certain probability.
Absolutely.
Do you have code available where you've done this already that we can cheat off?
I do not have anything in this slide deck, but I mean, really, it does come down to Python has a random class. Actually, don't use Python's random class. There are reasons not to use. Neuron has a better one. Because Python's random class, the reason that I say that is Python's random class is not designed for scientific computing. That's not the purpose of it per se. And so Neuron uses this thing known as random 1, 2, 3. And random 1, 2, 3 is a parallel random number generator, and it allows you to generate consistent randomness, whether you're running on one processor or 100,000. And actually, Salvador, are you here? Do you have an example of this in your stuff?
Yes, I think so. We do use that random number generator. By the way, Robert, just to let you know, there was an error in the schedule. So this session was set to 2 hours and 20 instead of 1 hour and 20, which was what we intended to do. So I corrected it, but you can keep going for as long as you want. And what we did is just change the exercise time, which was supposed to be 6 to 7. It now goes from 5 to 7. So you can use that time until 7 today, the same as before, however you want.
Oh, okay. Cool. I will keep talking until I run out of slides, and then we will move to the exercises.
Perfect.
Okay. So does position matter? And so sometimes it does and sometimes it doesn't. You're going to have Sometimes you want to construct models wherein connections are based on an axon passing near a dendrite. And so you grow the morphologies randomly, as was discussed. And then you just say, well, if it comes within a certain distance, we're going to connect it. There's a model by Michele Maiori from early 20-teens that does this and grows these olfactory bulb model. Connections based on cell-to-cell proximity, same idea. Extracellular diffusion, obviously, if a cell is near another cell and the one cell is affecting concentrations in the extracellular space, then the nearby cell is going to be more affected than one that's further away. And again, and I mentioned this sort of, if you're communicating with other humans, it is sometimes good to not, you don't want things overlapping, right? It's easier for other people to understand it if they're not used to this. So position can matter. All right, finally, well, no, not even, sorry. But nonetheless, we want to talk about, we now have cells, we now have the morphology, we have a discretization, because we can do that with NSEG. Let's add some ion channels, all right? So we have ion channels, let's say from a mod file. So Neuron comes with a couple that are built in. So there's Hodgkin-Huxley. This is H.HH. There's a passive conductance, so leak, H.Pass, PAS. And so if I have a conductance, let's say H.HH. So this is all the Hodgkin-Huxley dynamics are abstracted away into this entity H.HH. I can take that and I can insert it into an apical section. And then that's going to put all of those dynamics in that location. I could also pass in a list of sections. H.HH insert, and this would put it in the apical and the soma and in the basal dendrites. I could insert it in H.Allsec. H.Allsec is all the sections. All right, so this would put it everywhere in my entire model. All right, so that's the idea. If I have Hodgkin-Huxley, H.HH, then I can put it wherever using the dot insert. And so those are the only two ion channel methods that come with Neuron built in, but there's hundreds more that are available in ModelDB. Just look for all the mod files in any of these models, and then you can combine them. You can download them. You compile them with NRN-IV modal, or in Google Colab, it's !NRN-IV modal. But fundamentally, what you have here is that these are, the H.HH encapsulates all of those equations, right? And everything except for the cable theory part of it, right? H.HH is going to encapsulate all of the dynamics, the sodium channels, the potassium channels, and that's it. And so, just to give you a sense, let's look at one of these guys, maybe. Okay. So here is. You guys see that? Do you see GitHub?
Yeah.
Okay. Yeah. So this is the tinyurl.com/hh mod file. So this is actually what's happening, the code that's running the Hodgkin-Huxley channels. And you can look at this, and there's a lot of stuff here, most of which you don't really need to worry about. But if you look at this, it's got this thing called a suffix, and that's HH, and that's how Neuron calls it HH. If the suffix was cow, Neuron would call it H.cow. We can associate it with certain ontologies. I'm an informatics professor. I have to have ontologies in here somehow. But that just represents this is a sodium channel and potassium channel. It's going to use the sodium ion. It's going to use the potassium ion. This is how Neuron says, oh, well, I better keep track of sodium. I better keep track of potassium. I can have equations, but fundamentally the rate m prime, here's my derivative block. M prime, the rate of change of m, is going to be m infinity, so my limiting value minus m divided by m tau. And similarly for h, and similarly for n. And so then there's all these equations that go with this and calculate the various time constants and the limiting values of all the gating variables. If you've seen Hodgkin-Huxley, hopefully you've, nope, just kidding. If you've seen Hodgkin-Huxley, hopefully you've seen these variables before. But so this is the structure. And like I said, there's hundreds of these things that are available in ModelDB. It's a great resource to go and find something that, this is kind of like what I mean, one of the easiest things to do, right, is to find something that's kind of like what you need. And you're like, oh, this is the right equations, except the time constant's different or something like that. Just go find something, modify it, put in the equations. You can put it, it's pretty easy to adapt these things. And so these you can specify arbitrary kinetics, right? So H channels are different from sodium channels, but you know, sodium channels have many different subtypes. You can find all of these subtypes in ModelDB. Channelpedia is another resource that has mod file representations of various various channels. So we can do this with, you know, there's likewise, there's ion channels. So there's ion channels that are sort of distributed everywhere. There's what's known in Neuron as point processes, which are local events. So imagine that I have a synapse. And so this is one of the synapse models that comes with Neuron. It's very simple. It's a thing called, it has a name instead of a suffix. It's called a point process, DXPsyn. And fundamentally all it does is it has one variable that decays at a rate that's proportional to its current concentration. If you remember from your Diffie-Q, that's how you get an exponentially decaying curve. And so what happens is every time an action potential, every time this synapse is triggered, it goes up by a certain amount. When the net receive happens, whenever there's an event, it goes up. Its value G, its conductance, goes up by a certain amount, and then the conductance decays exponentially. And it gets a new synaptic event, and it goes up by a certain amount and decays exponentially, and so forth. And it so happens that because of the wonders of math, one synapse receiving multiple events with exponentially decaying dynamics is the same thing as having generates the same total amount of current as two synapses receiving events separately. You can ask your Diffie-Q teacher. But that's only true for exponential synapses, but it is true in this particular case. So in any case, so mod files are how we define all of these things. We can load them into Colab in any of a number of ways, by using GitHub, by using a wget. There's a graphical way of uploading files. There's lots and lots of ways of getting them into Colab. And then once they're in there, you can compile them with Internet IV model. But fundamentally, mod files are how we're going to express channel kinetics. There are other ways, but they're sort of the main one. You may have heard of a thing called InModal. Sorry. You may have heard of a thing called NeuroML. NeuroML, one of the things that NeuroML does is it provides an export to mod files. So if you have a mod file if you have a channel mechanism that's expressing NeuroML, there's a library, it's called JNeuroML, or there's also PyNeuroML that can convert it into a mod file for you. But for our purposes today, everything that we're going to do is just Hodgkin-Huxley and passive, because it covers what we need. So any questions about channel kinetics and getting them into Neuron? All right, so these points. So if I have a point process, it's a current clamp, so H.I clamp, and I want to point, or a synapse, right? And I want to put it in a specific place. When I create it, I just create an instance of H.I clamp, and I pass in the location. So soma of 0.5 is going to put a current clamp at the center of the soma. And I can always go back and get the segment, and then from that I can find out the section and all that jazz. But fundamentally, if I want to put something, put a point process like a current clamp in a location, I just pass the location into the constructor. setting and reading parameters. I'll skip this, it's in the slide, but the point is you use dot notation, right? So if I have a segment, segment.hh, and then from that I can access all of the dot conventions. So this is the GK bar, this is the average potassium, sorry, the maximal potassium conductance of the Hodgkin-Huxley channel at the 0.2 location on the apical dendrite, and so forth. So it's just this, the regular old point notation, if you've seen that Python classes. Cool. You can set and read in, say, Celsius. So Celsius is h.Celsius. You can loop over things. We've already said that. This comprehensions are great. Okay, so we now have we now know how to make a cell, define our morphology, insert ion channels, do our discretization. Let's actually record something. So fundamentally, the next step is going to be the instrument model. We're going to record it. So let's say that I want to record at a specific location. So I'm going to construct a vector. Vector is just like a list, right? I'm going to construct a vector. My vector is going to know to record, let's say, the X location on the axon. So some locations, membrane potential. Or time. Time is normally h.t. If I want to record it, remember we add this underbar ref. So I'm going to record both the membrane potential at some location on the axon and time. And I'm recording time here because otherwise it doesn't mean anything if I have a whole bunch of voltage values and I don't know what time it is. You may think that this is pretty, and so Neuron, by the way, you could sample, it could be that time is sampled evenly, or you could have told Neuron to, you know what, Neuron, I trust you. Figure out how I should do the time steps. And then Neuron will be clever about it and say, well, okay, you've got an action potential going on here, so I better use small time steps so I can capture that curve of the action potential. And then when you have the cell is basically chilling, returning to rest, oh, you know what? You're good. I can use big steps. I don't need to calculate a whole lot of points because nothing's happening. And so Neuron can be smart enough to do all of that calculation for you. And the nice thing is that lets you control numerical error if you're into that sort of thing. And it's also sometimes it speeds things up, but more importantly, it lets you constrain the numerical error. So record time. That's the punchline. The other type of data that you might want to record is you might want to record when a value crosses a threshold. So if you think about it, an action potential. Well, how do you decide when the cell's fired an action potential? Well, one way of doing this is to just sort of monitor a location. I'm going to look at the center of the soma, and if the center of the soma crosses 10 millivolts, let's say, it's an arbitrary choice, could be a different one. But if it crosses, let's say, 10 millivolts from below, because crossing from above is different from crossing from below. But it crosses 10 millivolts from below, I'm going to say that's when the cell fired, because it's not going to get up to 10 millivolts without firing an action potential. Right? If the cell's that depolarized, it's going to spike. It is spiking. So let's define the time of the spike as when it crosses 10 millivolts. Or here I said 0 millivolts, whatever. And so the way that we do this, we can set up a list, a vector here of spike times. We're going to record all the times of the spikes. We're going to use this object in Neuron called a netcon. You'll see more about netcons later, but I'm going to monitor a certain location. So the 0.1 location on the axons, membrane potential. And this is all kind of going to be formulaic. It's going to be common none for reasons that I'll explain in a moment. And then I'm going to also need to specify the section. So it's a little redundant, but in any case, h.netcon axon 0.1 pointer. And then I'm going to specify the section. I'm going to monitor the threshold whenever it crosses 0 millivolts, and I'm going to say I'm going to record that data. Anytime that it crosses 0 millivolts is going to go in my vector spike times. So if it crosses from below 0 millivolts at time 10, That'll go in my vector. If it goes up, gets up to 9, then turns around, don't care, but then it crosses my threshold later, I'll record that as well, and so forth. So I'll get a list of all of the times that the cell's fired an action potential, right? So I don't necessarily care about the membrane potentials. I might just care about when the cell spikes. In the context of a network, by the way, if you don't have gap junctions, under a lot of conditions, if you just have chemical synapses, right? In the context of a network, if I know where the cell starts and I know every time that it gets input, then I don't even need to know anything about the rest of the network. I can just reconstruct that one cell's behavior based on all of the inputs coming in. So really, saving the spike times allows you to reconstruct the entire dynamics a lot of the time. So it's really useful to say the spike times. By the way, so this, you're wondering why I'm calling a netcon a thing for recording spike times? Well, think about it. Detecting a spike is the first half of transmitting a spike. So a netcon is a device for connecting a network together. Told you there's usually a reason for the name. And so what that means, so then now what's the none for? Well, the none means I'm not sending this event anywhere. I'm just going to eat it up. But if I were to connect that instead of to a none, but to a synapse, like an EXP send, well, then it would be received by the synapse and then it would process it and do whatever. All right, but more on networks later. All right, so I can record the cell. I can construct the model. I'm basically there. One other little pesky detail. If I want my cell to do something, I need to give it some input because otherwise it's just sitting there. So how do I tell the cell to do something? And I was thinking about this last night, I guess, and I came up with 3 ways of telling the cell to do something. If there's another way to tell the cell to do something, Neuron probably supports it. But here's the 3 most common that I could think of. All right, let's just say, well, if I want to specify the membrane potential, if I'm going to say I'm going to start at time 0 with a membrane potential of, let's say, -20 millivolts, that's pretty depolarized. If I've got Hodgkin-Huxley or any reasonable set of ion channels, it's going to trigger a spike. And then if there's a network, if I got 1 spike, maybe I'll get more. Maybe it'll do a thing. Cool. So that would be one way. I could just explicitly say summa 0.5.v is 10 millivolts. I'm going to start out at a certain point with it's depolarized. It's going to fire the spike, and then interesting things happen. All right. I can also use a voltage clamp, and Neuron provides a couple of different voltage clamp mechanisms. An SE clamp is a single electrode mechanism. A V clamp is a 2 electrode voltage clamp situation. And so for those of you like me who came in from a more like a mathy sort of way, engineers probably know all this. But for those of you who came in from a mathy perspective, here's the thing. When you do an experiment, when you record a cell, like an actual cell with an actual electrode going in, that actual electrode has resistance. It has property, it has a capacitance. There's effect. The values that I'm recording are not the membrane potential that would be there if I wasn't recording it. It's slightly perturbed. And Neuron allows you to build, and I know Craig is working on a lot of this, Neuron allows you to build arbitrarily complex electrical circuits to monitor the effects of, I don't want to know, I want to know what would be measured. Because if I have my cell do the behavior that was measured, then my cell, if I were to measure it, would not be giving me the same results, right? So I want to actually have the measured value match the measurement value, not the other way around. And so that's why all of these little pesky details matter. So if I'm doing a voltage clamp, conceptually, a voltage clamp says, let's say that I want what happens when I force the cell to be 20 millivolts. Well, it's not mathematically forced to be 20 millivolts because there's a wire going into the cell. That wire has a resistance. It's not clamped at exactly 20 millivolts. It's attempts to be clamped at 20 millivolts. But there's some time constant. There's some dynamics. And those things matter. So anyways, that was my rant about physics mattering. But in any case, so you can specify voltage clamps, you can drive currents, you can do all kinds of things. I have an exercise that lets us play with some voltage clamps. So I'm showing this as if they're constants, but you can also use vector play to play. If you have a time series, you can play back a voltage into the time series and into the voltage clamp and force a sinusoidal current going, force a sinusoidal membrane potential. Why not? You could do that. You do the same thing with the current clamp, right? You could say, instead of saying I want the cell to be at 10 millivolts, what if you say I want to inject 1 nanoamp of current into my cell? One nice thing that you have here that you don't have in a wet lab experiment is you cannot kill the cell. So if you want to try, and get a response, like there's no harm in trying a bigger number to see if something happens. You're not going to break your experiment. And the other main way that you can get some input going in without getting really sort of wonky is to talk about synaptic input. So like in a wet lab experiment, you might trigger some axons and then they trigger the cell that you're actually interested in. So we can do this in Neuron with what's known as a net stem. And a net stem lets us stimulate the network. And so what we do there is we can say, well, I want a certain number of spikes, in this case 1, but it could be 5 or whatever, and they could happen at a certain interval. And that interval could be deterministic. If noise is false, that means it's literally at whatever interval you have until however many spikes. Otherwise, it's according to a Poisson process. There are good mathematical reasons to think that Poisson processes are the right statistical model to use. Ask your favorite statistician. But in any case, so we can do this. If we want to just get something going, maybe just one input's going to do a trick. Okay, so we have a cell. We have a cell. We can record it. We can poke it to get it to do something. Let's run it. That's all that's left. Except I'm not on the right screen. Okay, that's all that's left. So in Neuron, we've already done there's std run.hope to load everything. So we're going to initialize it. It's just going to say what the initial conditions are. H.F initialize is the way to do this. You have to do F initialize. You have to initialize your model, or it's not going to do anything meaningful. But so let's say it's going to be negative 65 millivolts everywhere. If your mod files are designed correctly, they will go to steady state at whatever initialization is specified. If they're not, they won't, but you know. So in any case, it's going to set up all of the initial conditions. You can define arbitrary initialization rules using an H.F initialize handler. Check out all of the docs. I mean, I know I'm talking for a bit, but there's a ton more to Neuron than we're going to have a chance to talk about. But so in any case, you load the library, you initialize the simulation, and then you say go. And that's it. And it's going to run until, in this case, 10 milliseconds. Or if I said 20 milliseconds, it runs until I'm 20 milliseconds. There's a different function. It's called psolve that does the same thing in a parallel context. NetPyNE, so for the purposes of this course, we're only going to talk about parallelization with NetPyNE, and it's just going to do all of the right. It's going to do the right thing for you. You could also advance one time step at a time using H.F advance, but that's rarely necessary. There's lots of other things you can do. You can get events at certain times and so forth. And that's it. So we now have a simulation. We've recorded it. We've built up our cell. We've built up our virtual organism. We've instrumented the simulation. We've poked the cell to get to do something. And we've ran the simulation. So now in principle, we have all the data. Just as an aside here, if we are concerned about accuracy, or if we want to make sure that our model has converged, we can reduce the time step by setting h.dt to a smaller value. By default, like I said, it's fixed step, 1/40th of a millisecond, but you can change that. You can have it do variable step integration. You can specify the tolerance if you're doing that. You can increase the spatial resolution, as Bill said, to see if it's spatially converged. But fundamentally, let's look at an action potential. All right. So what we have here is our first action potential of the day at 5:16 p.m. All right. So again, this is very, very sort of straightforward. This is the entire model. This is done with Matplotlib, but it's the same thing with Plotly or whatever graphs. So from neuron import H, cool. Always do that. Easy enough. Load some units. Okay, that's reasonable. Helps us be clear about what we're talking about. Load Matplotlib as a graphics library. Cool. We want to make a picture. Need a graphics library. And then I'm going to load std_run.hoke. Going to do that. That makes sense. It's my run control library. Awesome. So first 4 lines, good. I'm going to create a section, call it a soma. It's going to give it a length and a diameter. Cool. I'm going to add some channels, Hodgkin-Huxley, h.hh. I'm going to insert those into the soma. Done. I'm going to give it a current clamp now. And I'm going to inject a current of 1, I don't have units here, but it's 1 nanoamp, into the center of the soma, starting at time 2 milliseconds. And I'm going to do this for 0.1 milliseconds. And then I'm going to record my time. So I'm going to create a vector and record h.reft, that's always time. And voltage, I'm going to create a vector, record center of the soma's membrane potential. Remember the underbar ref for the recording. If you goof and you type .v instead of underbar ref v, it'll yell at you. If it yells at you, think about what you did and go with that. All right. So then we initialize our simulation, we run it, and then during the course of the run, those vectors are automatically updating. And then we plot it, and we look at a pretty picture, and there's our action potential. Does that make sense? All right. So just as a slight example, so slight generalization of this, suppose that instead of having 1 current clamp, I had many current clamps. Well, I can do that with a for loop. Let's make them all the same, except 1 at time 2, 1 at time 13, 1 at time 27, 1 at time 40. This is arbitrary choices, but why not? So I create a whole bunch of current clamps. I inject them. Cool. I'm going to record time and voltage. That's not changed. All right, now I can monitor. I don't have to do this, but I want to monitor the spike times. So I'll use netcon, as I showed before, right? I'm going to monitor spikes at the center of the axon. It's going nowhere. Section is axon. Spike times, I need a place to put it. I'm just going to record, my netcon's going to record all of the events in the spike times. I'm going to initialize my simulation. I'm going to run it. I'm going to print out the list of spikes. So I got a spike at time 3.225. All right. That's a bit after 2. That makes sense. I got a spike at 28.2. Well, that's a bit after 27. That makes sense. I got a spike at 41.7. That's a bit after 40. That makes sense. But what happened to my input at 13? Why the sadness? Why didn't it spike there? It's the same strength of a current injection. What went wrong?
Refractory period?
Refractory period. All right, the cell just wasn't ready for it. That's fine. I'm not going to rush you. All right, and that's the core of it. And you can imagine if I have a network of neurons, I create a cell, create a couple of cells. Going to create a soma. It's going to have, I'm going to inject Hodgkin-Huxley, insert that. I can add a synapse. If I'm having a network, I'm going to have a synapse. It's going to be an EXP syn. Again, exponentially decaying synapse. So it has some time constant with which it decays. Cool. It has some reversal potential. That's it. By the way, what's the role of the reversal potential on the synapse here? Or let me put it this way. What's the difference between a synapse that is excitatory and a synapse that is inhibitory?
The ions.
The direction of the current?
Yeah, the direction of the current. It was, right? So if the reversal potential is high relative to rest, so 0 is very high relative to rest, most of the time it's going to want to pull the cell up. If the reversal potential is lower than rest, it's going to want to pull the cell down, right? So the E, the reversal potential, is going to shift the effect. Is it an excitatory synapse if it's above rest, basically, and an inhibitory synapse if it's below rest? All right, but in any case, so I can create my synapse. I'm going to put it at a specific location. It's got a reversal potential that makes it excitatory. I'm going to create a synapse. Now, again, so it's a netcon. It's got a source, which is this membrane potential. And now it also has the synapse that's delivering to. It's going to deliver after a delay of 1 millisecond. Why is there a delay, by the way? There's the in-universe explanation, and there's the out-of-universe explanation.
Is it the amount of time it takes for the vesicle to be released?
Right. There's always going to be, so once the cell's fired an action potential, it's going to take time. It's going to take time to propagate down the axon. If the cell's not pathological, that's going to at least be stereotyped. It's going to be consistent. If there is a pathology, that's a whole nother matter, and you do want to simulate the axon. But it's going to take time to go down the axon. It's going to take time to release the vesicles. The vesicles are going to take time to mosey across the synapse. It's going to take time to bind and trigger the current. Right, so all of these things take time. It so happens that this turns out to make things very, very convenient for parallel simulation because it means that I have 1 millisecond to get around to telling other compute nodes that the cell's fired. I've got a positive amount of time, so I don't have to communicate every time, and that's what makes all of this very fast. And it has a weight, like how strong is the synapse? And I think that's sort of self-explanatory. And then so boom, so you construct that, you can record both voltages and plot everything, and then so we see the first guy fires, and then after delay, the second guy fires because of the excitatory input. And that's the basics of chemical synapses with neuron. Just finally, just as a couple of other notes, if we want to store data, load data, pandas is great. You can do it however you want. Basically, you can do anything with a vector that you can do with like a NumPy. Well, you can do a lot of things with a vector that you can do with a NumPy array or a Python list. Okay, so just go ahead and throw them in a data frame for pandas and dump it to CSV file. You can use pandas to read back in CSV files. Pandas is great because it also talks to databases. It talks to Excel files. It does everything. It's a little bit overkill for this problem, but it does at least allow us to read and write CSV files or whatever. And then so we can analyze it with however we want. And so thus concludes my sort of intro to this is how we do basic neuron. I have a couple of other notes, but does anybody have any questions or comments on any of this? Okay. By the way, if anybody's excited about all of this and wants to get involved and wants to help shape the direction of neuron itself, we do incidentally have developers meetings every third Friday of the month at 10 a.m. Eastern, 1600 Central European. And we have the agendas on the Neuron GitHub. So We've got a bunch of resources. Like I said, Read the Docs is the place to go for the Neuron documentation. We've got the forum, and we've got the models. There's a bunch of models on ModelDB. And with that, if there's no questions, we can move to some exercises and trying to actually do something. Again, these slides, including the exercises, are in the Google Drive that's linked on Slack. Salvador or anybody, did we figure out if we can do breakout groups?
No, we can't. So I've been trying and following the instructions. I don't see the option that they say. If anybody knows how to do it, please let us know. But so what I suggest is either using Slack, just in the chat, or you can have one-on-one meetings, or we can create individual Google Meets for each breakout room. And you can just let us know who wants to do that, and we can create them for them.
All right. So
and Robert, if you want to leave 5-10 minutes break, like coffee break or something before you start, feel free.
That sounds good. I've been talking for a while. I'm sure everybody's sick of it. But here's the deal. There are 4 exercises that are on that are in the slides here. The first one looks at current clamps and propagating action potentials. The second one looks at voltage clamps. The third one looks at net stems and synapses and wave propagation speed. And the fourth one is our buddy C91662. So do any of the students have a preference for how we do this? Because I certainly, here's the thing. I want you to end the day with a copy of a solution to everything, right? Which I have, so that's an easy thing. But I would like you to actually play with some stuff too. So does anybody have any idea as to how to do this in a world where we don't have breakout groups? All right, we'll ponder over that for the next 10 minutes or so for coffee or whatever break, and we'll come back and try and figure this stuff out.
I think you should upload it to GitHub, and then we just clone it, and as we did to and perhaps fork it and submit the answers, right?
Well, so I guess I was kind of hoping that people could discuss a little bit.
Yeah, what if we leave this channel open and people start working and can talk if they have problems, and if we need to have a breakout group, we can form a separate Google Meet for that?
Okay, how does that sound? So we've got Slack. We've got Slack. We can ask questions on Slack. We'll do this, and then I will leave you alone for like 15 minutes modulo any questions that get asked out loud or anything that gets asked on Slack. And then I will start rambling at you again about how things are going and addressing any issues and solving it. How's that sound? All right.
Sounds good. Thank you.
Yes, you might as well quit recording, Salva.